author, Said Talebi. Said, okay, Said, you here. Said will be talking about tolerance compliance management using terrestrial laser scanner.
Hello, everyone. Yes. First of all, thanks very much for to the organizers of this event and also the reviewers for selecting this paper to be presented in the plenary session. The title of this paper is Tolerance Compliance Measurement using Terrestrial Laser Scanner. My name is Said Talebi. I'm a lecturer at University of Huddersfield. The other authors are Professor Lori Koskela and Professor Patricia Zoutopoulos from University of Huddersfield. Before going to the main topic, I would like to first define a term that is used in this paper. What does actually geometric tolerance mean? To us, for instance, when we have a concrete slab, when it's subject to load, it deforms over the time, right? So you've got some permitted deviation for that deflection, right? So that's permitted deviation in the shape, in the form of that component is called geometric tolerance. So when you say geometric tolerance, you mean any limit that applies to the shape of components. Then we've got laser scanner for those, just to avoid any confusion. This is a laser scanner. Basically, it transmits billions of laser points in a second. The laser beams hit the object and return to the instrument, and then it gives you 3D data sets. So this is, for instance, an example of a building that we scanned, and the second one is an example of a warehouse after we scan it. Fixing tolerance problems are very costly and laborious. There is no really research that really quantify the magnitude of tolerance problems, but this is believed that more than 10% of defects in construction are related to tolerances, more than 10%. And more than 5% of construction costs are related to tolerance problems. For instance, in one of the projects that I was involved, it was £21 million project, and that project was delayed 4 months only because of tolerance problems. So actually fixing those tiny parameters are time consuming, and those tiny parameters actually do make difference. This is generally believed that one of the methods to improve tolerance management to avoid tolerance problems is to improve inspection methods. But what is the problem with the existing inspection methods? Like when we are talking totalization or dump level, they are very time consuming and they are very laborious because they most of the time require the direct contact with the component, or sometimes they are destructive. For instance, when you want to use totalization to measure flatness of concrete slabs, it may take you weeks, days to do it, right? It's already late. If you imagine that you want to measure the flatness of a building, concrete slabs of a building, and it takes you 7 days to do it. It's very time consuming. The other thing is communication, how you are going to communicate those results, for example. This is a survey result from a project, from a warehouse. 2 site engineers surveyed the same place, right? So, and after sometimes we put the surveys next to each other and we realize that one column is, common in both surveys. The first surveyor, so I'm talking. indicated by a red arrow. The first survey here shows that the column, the one arrow towards south, 10 millimeter, and the second survey here shows, has written one arrow towards north. So we were just wondering whether we should, what does it mean? Does it mean that we need to move the column 10 mil, towards south, or it means that it's out of position for 10 mil and it should be actually pushed towards north? You see, so communication of surveys, the findings by using conventional methods is again problematic. So general conventional methods for inspection are ineffective, time-consuming, and laborious. What is the research problem for this paper? When we look at the literature that they are around there about using laser scanner, there are different areas that they discuss. The first one is, for instance, data acquisition, how you are going to obtain data, right? What is the method that you use to obtain data? The second one, how you are going to register that data. What does it mean? You've got several scans, how you are going to put them next to each other, right? To get that 3D data sets from all your building or project. Then how you are going, it's about how you are going to perform deviation analysis. So, for instance, how you are going to measure the flatness of concrete slabs, how you are going to measure the perpendicularity of columns. The last area of research is visualization and demonstration of deviation analysis. So you did the survey, how you are going to communicate that with your clients. That, for instance, how much your column is out of plumbness. And surprisingly, all those areas of research actually depend on each other. You see, for instance, if you want to get, when we are talking about tolerances, we are talking about plus and minus 5 mil, plus and minus 10 mil, 2 mil, right? So, and all those areas, acquiring data, obtaining data, analyzing, they have their own inaccuracy. So for instance, when you register data, your inaccuracy can be plus and minus 2 mil, but you are measuring a component that must be within plus and minus 5 mil. So you may be already 40% wrong. You may have like 40% error, right? So for us, it's very important to perform the deviation analysis to the highest level of accuracy. And when we look at all those separate research areas, they are very dependent on each other. Why? Because if you want to get a very accurate deviation analysis, you need to have perform the data acquisition very well. It really depends on the accuracy of registration. Also, the accuracy of deviation analysis is reflected on visualization and demonstration of deviation analysis, because if your deviation analysis is wrong, probably you are communicated to your client, wrong information as well, okay? So we need a formal process that actually link all those areas of research together. Which at the moment doesn't exist as far as we know. The other question is, when you go on construction sites, people are, concerned about two things, flatness and plumbness. But that's all? Do we have another type of tolerances, or it's just all about, plumbness and flatness? So that's something we discussed in this paper. Lean and tolerances. The tolerance, I would like to just point it out that Lean community is at the front line of tolerance management. Up to now, the work, the most extensive work on tolerance management has been done by Professor Iris Tomerline and her PhD students. and we are also working on tolerance management. And in this paper, we are using one of the foundational elements of Lean, which is process standardization. We all know process standardization is essential to continually improve the design of a process. Research objectives. We propose a standardized process that called tolerance compliance measurement, or TCM, using laser scanner, or TLS. As part of this paper, we have provided practical recommendations for capturing 3D data sets, how to practically capture data sets that you can make sure that your deviation analysis are to a good level of accuracy. And also, when you want to register data, as I said, registration means how you're going to put the scans next to each other. For that, you need to have a workflow. I've spoken to many people, many operators who use, laser scanning, and each of them has his or her own workflow. We propose a workflow that we call it a minimum viable workflow for data registration. It ensures that your data registration is to a high level of accuracy. And also, we investigated different software that exists in the market and to see whether they are appropriate to measure different types of tolerances. Then we also discussed different methods that can be used for visualization and this demonstration of results, and we explore whether they are effective or not. First, what are the different types of tolerances? We have developed a method called geometric dimensioning and tolerancing construction, or GD&T. That's a continuation. That idea comes actually from Professor Tomeline. I'm not going to explain that method in detail, but that method actually helps us to understand different types of actual tolerances that exist in the industry. We divided them into form, orientation, location, and profile. And for each type of tolerances, we have different characteristics like straightness, flatness, perpendicularity, parallelism, position, and profile of a surface. And again, for each characteristic, we have investigated what sort of application that they can have, and it's in the paper. For instance, for straightness, it can be used for controlling the deflection of beams. Or flatness, obviously, when you want to assess the flatness of concrete slabs or any other component. Orientation, perpendicularity, plumpness of columns. Parallelism, when two components, like when you have a doorway and two sides should be in parallel to each other. Location, position. Obviously, all the components have their own position. That characteristic is used when you want to check the position of components. And then a profile of a surface, which is mainly used to control the level, like the level of concrete slabs, level of roof, and so on and so forth. For this paper, we did a literature review. Also, I, as a field researcher, I've observed a firm that firm provides services related to laser scanning. They have a very, good advanced practice. Also, for around 2 or 3 days, I was in a software vendor company. They are producing actually software to perform deviation analysis. This is like to how I wanted to understand the best practice. Also, we have scanned a couple of different buildings, and we have used Faro Focus 3D. for capturing data sets. All the deviation analysis have been performed by Scene software and also an external additional plugin that was installed on Scene, and Cloud Compare, that is the open source software. I really recommend that to use it. It's free for everyone and it's easy to use relatively. Also, we have used totalization because we needed to get a coordinate system embedded with components. I'll explain you how. So this is this figure shows the tolerance compliance measurement using TLS. It's got 4 steps. The first step is acquisition of 3D data sets. The second one is registration of 3 data sets, deviation analysis, and visualization, demonstration, and deviation analysis. And we have sort of summarized all the recommendations that have been given in this paper. For instance, planning the scan path should be done as part of acquisition of 3D data sets, using totalization, setting quality and resolution parameters as part of acquisition of 3D data sets. And then we go to registration. We talk about following the minimum viable workflow, deviation analysis, finding correspondence, computing distances, and visualization. So the first one, acquisition of 3D data sets using TLS. So first we need to capture data. But the point is, I've realized that operators just go to the site and start using laser scanner without doing, without planning that. Whereas it is important to plan before going there. So we have proposed to use a scan map. This is an example of a scan map. A scan map is basically can be like a drawing, a floor plan that you use the position of scans with the corresponding scan number in the field, right? Those numbers, in red shows the position of scans, right? And those, blue lines shows the scan path. It's really essential. It's really helpful to understand what is the optimum scan path. It should be zigzag, right? So how you can do it, where you should put the scans in different positions, and it just really gives you an idea before going on site and capturing data. Then it's about reference targets. You see, again, it's very important to perform the whole process in a way that you get the highest level of accuracy, right? So we need to make sure actually the data is properly sized and leveled. To do that, we propose that we need to have like 3 or 4 reference targets. Those reference targets are short in yellow. There are 4 of them. And they should make a triangulation. That's the best way of putting those reference targets. By target, it can be checkerboards, white and black, or it can be like some spheres that you can put it. And then we need to use totalization. Why? Because we need to get a reference coordinates. We need to get coordinate system, and we need to assign those coordinate system with those targets. It's really help us to later, during the registration, to align those scans together. Then, again, during the acquisition of 3D data sets, it's really important to set the resolution and quality. We have proposed, remember, it's obviously when you have like a higher resolution and higher quality, then you have better accuracy, but the problem is going to take longer time. We need to have like a balance between the time that needed for, data acquisition and the level of quality and resolution. And it's better to have higher number of scans at lower setting rather than lower number of scans at higher setting. So we have proposed some settings that can be used, and then scanner and target placement, how they should be, put on the side. So we think that distance should be around 10 to 15 meter. At least we need to have a minimum of three targets in each scan. And then we have proposed a minimum viable workflow for registration. We have two types of registration: target-based and target-less registration. When you have target-based, you have some, checkerboards or spheres, or when you have target-less, you use some vertical components. So we have proposed that workflow, so anyone using Faro laser scanner, if follow that workflow, it's really helped to ensure that the higher level of accuracy is achieved. When I say level of accuracy, I mean plus and minus 3 millimeters. Then for deviation analysis, based on our observation, we have two types of analysis: sole point cloud analysis or point cloud versus point cloud analysis. When I say sole point analysis, like you've got a scan, we scan a place, right? We just analyze that scan. But when I say point cloud versus point clouds, when we overlay two scans on each other. In this paper, we investigated different algorithms to compute deviations. For instance, for sole point cloud analysis, we can use point to reference plane or point to reference line. And flatness and perpendicularity can be measured by that, and also straightness for point to reference line. Just to give you an idea, so the first one, this is like a point cloud, all of them in blue, so we can measure distance between 2 points. Or the second one is a one point cloud, but we define a reference line or reference plane, and we measure distance between that point to that reference line and that reference plane. And our findings shows that at the moment, technology just allows us to just do the measurement for certain type of tolerances. We cannot measure the perpendicularity, and parallelism and profile cannot be automatically controlled using the existing algorithms based on this categorization. Then it's a matter of visualization and communication. So the first one is a heat map. This is like a concrete slab, right? It shows those areas in red are 30 mil lower than those areas in green. So in few minutes, hours, you can get a holistic idea of flatness of your concrete slabs. Or the second one is a warehouse. I checked the plumpness of and columns. So the blue means that they are within the tolerance, and the last one, you see, buildings moves over the time, right? So I did the scan several times, and I overlay all those scans together. It shows that the camber of those beams are changing, and it shows whether they are within tolerance or not. So, and we use the straightness algorithm for that. So we define a line, a reference line under the beam, and we check that how much points are deviating from the reference line. So as a conclusion, we propose a formal and holistic method, term tolerance compliance measurement using TLS. We recommended some practical we propose some practical recommendations for preparation of scan map, placement of scanner and targets, and configuration of scanner setting. We propose a minimum viable workflow to achieve less than 3 millimeter deviation when we are doing the registration. For the deviation analysis, we categorize the existing algorithms in the market to sole point cloud analysis and point cloud analysis, and we realize that it's not easy to automatically control the plumpness profile and parallelism tolerances. And we checked how the findings can be visualized and demonstrated using deviation maps or numerically. Thank you.